Okay, I'd like to review stress and strain, and in particular, what we can get out of the stress-strain diagram. So at kind of the most superficial level, let's say we got some stress and strain. We've got elastic regions, and at some point we reach the elastic limit and we start having plastic deformation as well. We have some maximum, which is our ultimate tensile strength, and then it comes over here and it fails. This is the high point. It's our ultimate tensile strength. This is our elastic limit, but the elastic limit is not easy to find. So instead, we come over by what's called a 0.2% offset. So that's 0.002 strain. And we trace up parallel. And that point now is our yield point. And we characterize that as the sigma y. Our ultimate tensile strength, we also characterize as sigma yts, or sigma ts if you don't like the word ultimate. And our slope in the elastic regime, our slope is the elastic modulus or Young's modulus E. So that's one set of information that we can read from this diagram. But we can also talk about a material's resistance to deformation. One thing we can get is we can get ductility. And we're characterizing this as the amount of plastic flow at failure. So if we have stress versus strain, goes up, we've got our elastic, turns into plastic, and right here, just before failure, we could come down and we could say that there's a certain amount of this, a certain amount of it that is coming from the elastic contribution and a certain amount coming from a plastic contribution. Right? And if we keep pulling on the part, past there and it breaks, well, when it breaks, what's going to happen is the elastic part is going to shrink back, and we're going to be left with two parts which are slightly shorter than they were just prior to fracture. And that snapback has the slope of the elastic modulus. And we can say that this part is the plastic strain that's residual after fracture. And this part is elastic. And that's the part that's recovered upon failure. And we characterize the ductility in terms of the percent elongation after failure. So if we know the amount or the length of the part at failure, then that would be, and this is after breaking, minus the initial length divided by the initial length. And that's how we characterize ductility. Now, ductility looks a lot like, at least the way we drew it, looks a lot like we're taking the area under the curve, but we're not really. Talking about taking the area under the curve, now there is where we start talking about the energy. And one characteristic form of energy is the resilience. Resilience is a measurement of the elastic energy stored, or the energy stored elastically. So again, if we have our stress versus strain diagram, and say we're up here in the plastic regime somewhere, and we talk about how much energy is being stored elastically, well, we can go up to the yield point. So that's going to be our yield point. And if we look at the area under the curve, the area is the energy. And we talked about this in class, how this is because stress and strain are conjugate terms, so we wind up with an energy expression, or I guess in this case, an energy density. And we characterize the energy stored elastically, so that's why we're stopping at the yield point. We classify this energy as what we call the modulus of resilience. And your textbook is using a little UR for that. And that's going to be the integral of this to add up that area. So it's going to be the integral from 0 to the strain at the yield point, sigma dE. So here we're saying that sigma is a function of the stress is a function of the strain. And this is approximately 1/2 sigma y epsilon y. This is a triangle made by here. And it's not perfect, but it's a pretty good approximation for the modulus of resilience. And kind of lastly here, we have the toughness. And there's lots of ways to characterize this. People talk about it in terms of, the crack propagation in ceramics and Vickers hardness testers and whatnot. But here, we're just going to characterize this as the energy required for fracture. So that's going to be the area under this curve. That gives us the toughness. Okay, and it's the area right at fracture. So it is both the elastic and the plastic strain components. To the next concept I want to discuss with you, and that is the Ramberg-Osgood equation. So the Ramberg-Osgood equation is really an idealized stress-strain curve. And this stress-strain curve, let me write it this way. E is equal to sigma over E plus K sigma over H 1 over N. And this is our Ramberg-Osgood equation. It's not a perfect expression, certainly, but in many cases it does accurately represent the elastic and plastic portions of the stress-strain curve. And where it comes from, really, it comes from saying that E is equal to an elastic portion and a plastic portion. So this elastic strain is from our Hooke's law. So there's an E there. So this is there. And our plastic strain is coming from a power law. Which means that EP is equal to sigma over H 1 over N. And that goes into here. And I've got this scaling factor K, which can also be used to shift these relative to each other. This N is our hardening exponent. And it's the same N there as in there. So it's in this power law. And what makes this Ramberg-Osgood equation so useful is that if you have an analytic expression, then you can fairly easily do the integrals for talking about things such as toughness or resilience. So let's say that I gave you a Ramberg-Osgood equation, and I said, okay, well, given that the Young's modulus is 250 gigapascal, which is 250 times 10 to the 9 Pascal, and given that this H coefficient, 8.694 times 10 to the 8, and I'm not going to talk about where these come from. The details of the derivation and what these mean, you can look up elsewhere, or you'll certainly see later in life. K equals 1, and a hardening exponent let equal to 0.25. So given these four, that gives us E, K, H, and N. So now we have epsilon as a function of sigma. Now the challenge here is, of course, we have epsilon as a function of sigma, not sigma as a function of epsilon, right? So we have an expression which essentially is going to look like E versus sigma. And it's going to have this shape to it. But that's okay. And it's also not very easy to invert this expression. But let's look at a problem we can solve. Let's say that we have these. What is the toughness given abrupt failure at sigma u equals 400 megapascal, or 400 times 10 to the 6th Pascal. Well, we've got the equation, and we've got the coefficients, which means we can substitute this, or let's call this, sigma f for failure. We substitute sigma f in, and that's going to give us epsilon f is equal to 0.0464, which is, saying we've got about a 5% elongation, which is not unreasonable. So we now have sigma f and epsilon f, and now, as I said, we really would like to have stress versus strain. We really want to have this area, but we don't have sigma as a function of epsilon. But we do have epsilon as a function of sigma. So we're basically turning this around, and we can determine that area. So if we take the area of this box and we subtract the area from integrating epsilon as a function of sigma, we can determine the toughness, which is this area. So let's do that. The box is defined by our failure points. It goes from 0 to 0.0464 and from 0 to 400 megapascal. So our box is equal to 0.0464 multiplied by 400 times 10 to the 6th is equal to 1.856 times 10 to the 7 Pascal. And then this area is defined as the integral from 0 to sigma f of sigma over E plus K sigma over H 1 over N d sigma, which is sigma squared over 2E plus K sigma over H 1 over N over 1 plus 1 over N evaluated at 0 and sigma F, which when you substitute in all the values from the previous page, we wind up with 3.905 times 10 to the 6th. So taking 1.856 times 10 to the minus 7 minus 3.905 times 10 to the 6th, we get 1.466 times 10 to the 7th Pascal. And this is how we're expressing our toughness. So this is an example of how the Ramberg-Osgood equation can be used to approximate quantitative information out of these stress-strain curves.